Okay, so thank you very much. I have a long name, but typically outside Portugal, I'm just João Sousa. So actually, I have two presentations. This is my first one, and the second one is about the UMR project, just a very short presentation. Then after that, we'll go into questions. So today I'll be talking about exploring dynamic features of the ocean with coordinated robots. And this is the outline of the presentation. So I'll start with some ocean observation challenges, an overview of LSTS, discuss operations at sea. I'll go into more detail in what regards the exploring fronts with multiple robots SOI crews, and then finally some conclusions. Ocean observation challenges. This is the reason why we're here. Nothing really new about this, the blue planet, but this is somewhat misleading. And all of Earth's water would fit inside a sphere that is not that big. So it's blue, but it's really a thin layer of blue. So this means that we have to be very careful with what we do in the oceans, or with the oceans, and we still don't understand much about what is going on there. Hence this quote from Walter Monk, who passed away recently. So we still don't know much about the ocean, and there are lots of interesting things going on in the ocean. I'm an engineer, so I'm not a scientist, so I'll just be kind of alluding to some issues or challenges in oceanography and marine biology. For example, the issue of energy dissipation in the ocean. So, for example, internal tides account for a significant percentage of energy dissipation in the ocean. Still, we don't know much about this. Another interesting fact, ocean dynamic topography. If you take a cut, a vertical, so north to south cut along the Gulf Stream, you'll get a drop of approximately 80 centimeters. Another problem, oxygen minimum zones. These are really becoming a problem. So basically fish tend to stay away from those. But interestingly, you have lots of microbes there. So people working in kind of microbes also are very much interested in this. I'm not very much interested in not having fish. Another important issue is to understand the structure of the flows in the ocean. I'll say a bit more about this. And then again, so I'm not a biologist, but going a bit deeper in what regards motivation for our developments, I borrowed these slides from Peter Gergis from Harvard University and also from Chris Schoen from MBARI. And so basically studies over time have established a few key principles. All life harnesses its energy from the environment. Some chemical building blocks are found in all known life, and the environment in which an organism lives shapes its defining characteristics. So understanding the environment is crucial to understanding what is going on with these guys. Our oceans harbors untapped biological diversity. There are approximately 2 million known animal species, but for microbes, it's even kind of it's quite different because there are likely hundreds of millions of different species. And microbes run our biosphere. Without them, the biosphere could no longer support life. And now some surprising figures. So microbes are found throughout the ocean, from the surface to the seafloor, huge numbers, and surprisingly, their weight, it's huge, and it's approximately 10 times the weight of all human mankind. So, quite surprising. Anyway, so this is motivation for some of our developments in what concerns ocean observation. Just one example. One challenge would be, for example, to follow a molecule of carbon dioxide from there to there on a scale of hours to months and to eventually years. So we need synoptic observations on large spatial scales. You need persistent observations. We need to go from the micro scale to the mesoscale. And you need to be able to find, track, and sample physical, chemical, and biological features of the ocean with adaptive spatial and temporal resolution. How to do that? You need coordinated observations, underwater, at the surface, from space. But this is not an easy task. Why? Because this is a remote and challenging environment. It's largely unknown. You don't have navigation aids in underwater, especially in the open ocean, no refueling stations, and it's a communications challenged environment. And at our lab at Port University, we've been trying to address some of these challenges. So we've been designing, building, and deploying autonomous underwater, surface, and air vehicles for networked operations. Applications include oceanography, biology, security, and defense. We've also been developing the software that allows all of these guys to work together as a team. And this is our vision for a sustained presence in the ocean. You may have seen this before, but I like it, so sorry, please abide with me. So you'll need lots of different assets in the ocean, and there will be lots of different interactions. Communication links, mixed initiative interactions, meaning operators in the planning and control loops. Vehicles may come and go if you're interested in persistent operations. Same thing with the operators. There's the issue of scalability. Right now, I think that we have a good kind of understanding, or kind of a good handle on the operation of, say, 10, 15 vehicles. What about 100? What about 1,000? We don't know how to do that. We're also using vehicles as data mules because you don't have permanent connectivity. There's also the issue of distributed computations. The issue of physical mobile locality. So making a difference between mobile computing and mobile computation. And in our vision, we would really like to treat this ensemble of assets as a system that has properties. Sorry. Okay. So we would like to treat this ensemble of assets as a system that has properties that are a function of the vehicles, a function of the networks, and a function of the interactions that you establish over them. So we would really like the system to have organization-like properties. This looks like PowerPoint engineering, but hey, we have been developing the vehicles, the software, and the tools and technology that will enable us to achieve this vision. And we are getting there one step at a time. We are not there yet, but we are making strides along these ways. In terms of vehicle systems, we have a quite diverse mix of vehicles. These were meant to be low cost and modular, but then again, cost is mainly driven by sensors, as Professor Vukic said, and also by other components. Long endurance, it's important for us, and common software, and also some common computational hardware. And we want these guys to be interoperable, meaning that they can talk to each other. This is quite unique because you typically don't find these in commercially off-the-shelf vehicles. And then we've been playing with some more exotic vehicles. For example, flying modem, so it's basically an octocopter that can take off and land from water and deep an acoustic modem in the water. In cooperation with some of our partners from Spain, we've also been interacting with the CubeSat that is in orbit and using that for communications. And now, I'll just to say something more about our flagship vehicle. So the Light Autonomous Underwater Vehicle, LAUV. So we got this National Innovation Award in 2006, and basically we have two main versions, and for each version there will be several configurations. Upper water column, and basically endurance can be 50-hour plus, and mapping. And there you can have camera, multi-beam, side scan. There's support for multi-vehicle operations, and then these are commercialized via OceanScan. Ocean Sousa is there. And in terms of operations, it's conceivably very simple. This was offshore from a Portuguese oceanographic vessel. You just need to make sure that there's water there. So that's the only thing that you need to make sure, because it happened before that people didn't pay attention to that. So basically, in connection to the LAUF, I've been asked by Annette Stoll from NTNU to present this slide about the Aileron project. So this is an aside on my presentation about the lab. And the objective of this project is to embed an imaging classification analysis control chain for plankton taxa classification on board a robotic vehicle, in this case, the LAUV. So there's in situ imaging, which is done with the SILCAM, which was developed by Emlyn Davis from Syntef. It was mounted on an LAUV. There's machine learning, there's hydrodynamics, and there's AI planning and execution. And the outcome is to provide biological oceanography with a low-cost tool to determine temporal changes in community structure, abundance, and dispersion of planktonic taxa. Now, going back to what we do in our lab, we've also been developing the open source LSTS software toolchain. So there will be a tutorial today. We have three main components: Dune, which runs on board; IMC, which is our protocol for communications. So in our networks, all nodes talk IMC. And then you have Neptus, which is basically the control interface. There's another tool, a more recent one, Ripples, which is basically a web server to support communications. There will be more about this soon. We've also been playing with onboard vibration in cooperation with Canaraja. So in some of our vehicles, we installed T-Rex that interacts with Dune. And plans are generated on board when new objectives are received or there's an error executing some of objective. One objective could be something like go to this location and take a picture, or surface every half hour. So onboard objectives, onboard vibration. We've also played with off-board planning, and one example came from an experiment that we did in the Azores with what we call Eroptus. So Eroptus runs on a ship, or it could run somewhere else, and basically generates objectives that are sent to all of these assets that we have in the water or flying. And then on board we have T-Rex that will take care of planning and execution control. Okay, so much about what we do in the lab. In terms of operation areas, we've been operating a lot. So we've been organizing large-scale exercises. We have deployments from shore, from ship, and also from manned submarine. We have over 1 day of operations per year. Last year, our AUVs did over 4,000 kilometers underwater, and our UAVs did over 200 flights, including a few crashes. And we've also been organizing the REP exercise in cooperation with the Portuguese Navy, and more recently with CMRE, since 2010. Several areas: expeditionary hydrography, ocean sciences, search and rescue, ASW, mine warfare, and standards for underwater communications. And we play with some cool assets. This is one of them, and you have here other assets. This year, the exercise became a NATO exercise, so it was much bigger, and we have some figures from this year. The exercise ended last Friday. So 15 days, 7 navies, over 10 companies, over 800 people, 9 ships, including a frigate, a destroyer, and 1 manned submarine, and over 50 ASVs, AUVs, and UAVs. So this was quite challenging and a bit messy, but still, that's how operations at sea kind of go. And now I'll spend most of the rest of the talk talking about exploring the STF front with multiple robots crews. This took place on board the Falcor and was funded by the Schmidt Ocean Institute. So you see there our team and the Falcor. In our team, so we had people from Portugal, from Spain, from Norway, and from the US. And we also had collaborators, for example, Syntef, that provided SILCAM, NASA Ames, that provided a sensor prototype for measuring DMS. I'll say more about this, and also MBARI. And the main goal of the cruise was to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. I'll repeat this several times because it is very important. And here's a video which was put together by the guys from SOI. We don't do this fancy stuff.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here, two masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation, and by doing that, we hope to establish some of the foundations for the future of oceanographic surveys.
Okay, now a few words about the OP area, the Northern Pacific Subtropical Front. And it's a sharp boundary where cold waters from the Arctic meet the kind of warm, salty waters from the south. It has a very strong salinity signature, but has a very weak SST signature, meaning it's very difficult to see from space using SST. It's even more difficult because it's mostly cloudy in the area. So, for example, for 2 weeks, I think we saw sun once. And it's relatively shallow, and it's located approximately between 800 and 1,000 nautical miles from San Diego. And there were some previous studies in the 70s and in the 80s using ships. So you see here some of the ship tracks, and here you see some data from these ship tracks. So in X, you have distance in the order of hundreds of miles, and in Y, you have depth. So there's a graph about salinity and a graph about temperature. Let's just look at the graph about salinity. You have some ISO lines there. And then you don't need to be an oceanographer, and there's one here, and at least there's more than one oceanographer here. Renat will tell you more about oceanography and AUVs. But you don't need to be an expert to notice that there's this kind of band there that is quite different from what happens to the left and to the right, which means that you have different masses of water there. And actually, this is basically the location of the northern subtropical front and the location of the subarctic front. So basically, we went after the northern subtropical front. So this is what we used. So we had the Falcor as a kind of a mothership for all of these assets. So we had 3 VTOLs, 2 quadcopters, 1 wave glider, 2 sail drones, 1 EcoMapper AUV from the University of Cartagena. We had 6 AUVs from our lab, some of them with 50-hour plus endurance, and we had 1 AUV from NTNU. In terms of software, we used Dune, IMC, and Aptus, and on the top of that, we used Ripples, which is our communications hub for data dissemination and situation awareness. So we had a web-based mission control center. We operated basically non-stop for 2 weeks, 4 shifts per day. We had operators in Porto and also on board the RV Falcor. This is a view of the mission control center. You had a planning view, a risk analysis view, a timeline view, and a data view. And this was the mission control center on board the Falcor. Our AUVs did over 2,000 kilometers, and the ASVs did over 10,000 kilometers for this experiment. Now, a bit deeper in what concerns what we've done. So how to address the complexity? How to go about finding, tracking, and sampling this big ocean front? So we came up with task templates, nothing really outstanding. This is an example of a few of them. Yo-yo flight, something very simple. Then again, yo-yos, but kind of zigzagging across the front. Keep in mind that the location of the front was not known in advance. And then having multiple AUVs kind of running sort of mowing the lawn pattern concurrently. And then a few questions that are worth asking. So posing, are these the right tasks? What about task coordination and sequencing? What about vehicle-to-task allocations? What about launch and recovery of AUVs? Or about CTD casts from the ship and also taking water samples? How to coordinate the whole thing? Now, let's talk about operations. The first challenge was to find the front. Why? Because as I told you before, it has a very weak SSE signature, and it's mostly clouded there. So it's very difficult to see from space. So we used one wave glider and 2 sail drones that were deployed into the area ahead of the ship arrival. And then we were looking at sharp transitions in temperature and salinity. We're also looking at data coming from some model outputs and also from Argos floats. And based on lots of different considerations, we had several oceanographers on board, marine biologists. We picked this area for the initial survey. And now I'll briefly discuss what we did in terms of planning operations for all of these assets. So basically, we had 2 ASVs that crossed the front near 30 degrees north. To the left, you see a track of a wave glider, and to the right, you see the track of a sail drone, and those cross the front pretty much there. So we picked this rectangle, which is pretty big, something like 50 nautical miles by something like 40 nautical miles, if I get it right, for our op area. At the time, the RV Falcor was there. Then what we did was the RV Falcor sailed to the nearest point in the area and then performed the north-south CTD survey. Very conventional. Then when we got there, we put 3 long-range AUVs in the water, and we started a kind of a going this way and sampling using yo-yos. While we were doing this, the Falcor was taking CTD casts, and we kept doing this, putting vehicles in the water, getting those off of the water, up until we covered the whole area. Then we deployed short-range AUVs along the front with biological sensors. We did the same thing with VTOL UAVs, basically with DMS sensor. I'll say more about this shortly, and with multispectral cameras. And we also performed CTD casts along the front. Now some results. So what you see here, you see AUV tracks color-coded by salinity, superimposed on a CTD image, the only one that we got during this cruise. And let me give you a sense for what you're seeing. So this red, kind of a blob, or kind of a, at the bottom, is basically the front. Then there's this red kind of a patch that is a filament that was detaching from the front. And here we measured currents of up to 2 knots, which is a lot in the middle of the ocean. And there's a very nice, let's say, correlation between our measurements and what we got using SST data. Now, kind of a 3D view of the front. We are still going over the data because we got lots of data, water samples, chemical analysis, and kind of a DNA sequencing and all that type of stuff. But one of the tools that we've used recently, and this was done by José da Silva also from Porto University, was to use finite size Lyapunov exponents to study what was going on there. And actually, this is quite, let's say, if you're in robotics, this is quite close to what we do, because we are talking about Lyapunov theory, and basically, we are talking about the way particles converge or diverge. So this is a product derived from satellite altimetry that gives you basically the skeleton of the flow and how particles converge and diverge. You can get to this product from the Aviso website, and this was not available at the time. Short video. So the op area was there, so this is the kind of scales are really huge. But I'll give you sort of a magnified version of what was going on there. So you have the finite size Lyapunov exponents there, and then superimposed on that you have AUV tracks color-coded by salinity, and you also have these arrows representing currents at those locations. And so you see a very nice kind of correlation between these currents and the location of the front and also of the measurements that we're getting. Same thing with SST data. So basically an important finding from this study was that you can conceivably use this tool to study this type of front. Doesn't say that we can use this tool to study ocean fronts, and Renato can tell you more about that, but in the open ocean, this really worked very well. We also used this prototype sensor developed by NASA Ames that was mounted on one of our UAVs to measure concentrations of DMS. DMS is a gas, it is a byproduct of biological activity. And basically the idea, this has never been done before, was to see if there was any correlation between concentrations of DMS and the location of the front. And here you have some results. These are very preliminary results. We are working on these with NASA Ames. We also performed automated front detection and tracking. This was done on the fly, on the ship. So we developed the algorithms and we ran those first on the Wave Glider, then on the RV Falcor, and then on AUVs. We also performed high-resolution coordinated sampling using AUVs with biochemical sensors coordinated with the Falcor and UAVs. So basically, all of these guys were flying information. The Falcor was not moving fast because it was kind of towing a CDD. And now some conclusions on the future of oceanographic field operations. Some comments by this guy from SOI.
So we take all these different systems that go beyond the footprint of what a ship can do. They can be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
So in summary, we successfully demonstrated a novel approach to observe the ocean with persistent networked vehicle systems. The front was located precisely as predicted. The easternmost segment of the front was studied in unprecedented detail. For the first time ever, a mesoscale filament of a major open ocean front was mapped with sub-mesoscale resolution using largely multiple AUVs. Some figures about operations. And the key message or take home is that systems and technologies demonstrated in these screws are applicable to other frontal regions as to other phenomena of the world ocean. Now some publicity before switching to the next talk. So we'll be organizing the Oceans 2020 conference in Porto, and of course, you guys are mostly welcome there. So now I'll switch to a very brief presentation about the EU Marine Robots project. So we are still good in what concerns time, right? So, and this will be a very short presentation. So I'll briefly talk about the H2020 Marine Robotics Research Infrastructure Network project, EU Marine Robots, or UMR. So we have 15 partners from 12 countries. And basically, UMR addresses the core topic, integrating activities for starting communities by mobilizing a comprehensive consortium of most of the key marine robotics research infrastructures in Europe to achieve the following. Open up key national and regional marine robotic research infrastructures to all European researchers and also to people outside Europe. An integrating activity must combine transnational access. So we are basically funded to provide access for free to people that can apply to the use of these assets. joint research activities, and networking activities. This is a sample of our research, infrastructures, quite diverse: AUVs, ASVs, UAVs, ships, test beds, and with lots of different sizes and flavors. And vision for this project is, so it's organized around the evolution of a network model. It's about connecting people. It builds on existing networks of the EU marine robotics community. It's synergistic with worldwide marine robotics communities. It's aligned with the strategy for development of European ecosystem for robotics and autonomous systems, and will underpin the development of next generation observing systems, and it provides a single entry point to EU marine robotic infrastructures. Goals, lots of goals, just a selection of some of these goals. So the provision of access to state-of-the-art infrastructures, to large-scale sea experiments, to data collected by marine robotic systems, and also to provide uniform training for users of the infrastructures, and also to enhance utilization of marine robotic infrastructures, which is exactly what you're seeing here at BTS. So BTS is a very important part of our project. Work plan, without going into details, started last year, 3-year project, 8 work packages. The first one is about project management, and the other ones are basically aligned with joint research activities, networking activities, and transnational access. So WP1 is about implementation of UMR. WP2 is about networking, communication, and dissemination. WP3 is about e-access to the infrastructure. WP4 is about training and education. WP5 is about integrated experiments. WP6 is about innovation to advance marine robotics, and WP7 is about multi-platform and persistent operations. Networking activities, what are we doing? Cooperation, articulation with national strategies and initiatives, and field training in summer schools. Then again, breaking the surface play a key role in this project. Curiously, the Pocan Glider School runs in parallel to BTS, and also the organization of demonstrations, tutorials, and roundtables. In what regards transnational access, so providing access to our infrastructures, 3 open calls. Calls 1 and 2 are closed. The results of call 2 will be announced in the next 2 days, and call 3 will be open during BTS. We have 2 modalities of access. First one is you can have access to marine robots operated by the partners. Second one is you can have access to collaborative sea experiments, and some of these will take place in the Arctic, others will take place in the Atlantic, and others will take place in the Mediterranean. Very exciting. About joint research activities, basically these are about improvements towards integrated EU research infrastructures. And these are some of the improvements that we've been talking about. For example, making systems more operable, the issue of interoperability, the issue of services that research infrastructures can provide, and access procedures and interfaces. And in terms of joint research, this is organized into 6 tasks. The first one is about advanced vision, acoustic, and manipulation systems. Second one is about cooperative navigation and control. Third one is about hybrid acoustic, optical, underwater communication networks. Fourth one, about advanced systems for under ice operations. Fifth one, enhanced underwater large system. And finally, the 6th one is about cooperative human marine robotic systems. So this is all I had to say about UMR, and I think that the key message and take home is let's work together. This is what UMR is about. Finally, I would just say, and I should have said it opening, that is really a pleasure and an honor to be here and to be a part of this amazing event. Congratulations. Thank you very much.